Okay, now it's going. Covalent compounds, what is the characteristic of those is that you have shared electrons. That is, if we take one of the bonds from that compound above there, where there is a hydrogen and there is a carbon, that they are both sharing these electrons, both of those atoms are. And since their nucleuses are positive, the electrons are negative, that attraction is what's holding them together. Now that differs from ionic compounds, where you would have a positive ion like we have in the sodium, and that's attracted to the negative ion we have in the chloride. So that's different than the covalent compounds. Now when we get to the coordinate covalent compounds, things get a little weird, because with our ionic compounds, it's easy to see that, hey, it's going to be a 1-to-1 ratio of sodium to chloride, because you're going to need one negative for every one positive. Or if we had a compound like calcium chloride, CaCl2, the calcium, 2 positive. The chloride, again, is negative, so you're going to need 2 of those to balance it out. So it's easy to see how many we're going to need of one part of the molecule to go with the other. Now, that doesn't exactly work over in the covalent, but we can do Lewis structures and make sense of the compound. But when we get to coordinate covalent, it gets a little weird, because in this case, we have a scandium 3+ cation. And then we have it surrounded by water molecules. So this would be one of the water molecules, for example. And with water, you should recall that they have 2 pairs of lone pair electrons. So you could sort of think about that as having an excess amount of electrons. So you could envision how that would produce a attraction or a bonding between the scandium and the water molecule. But the only thing is, you've got 3 positive charges on the scandium, but if we look up here, we have 6 water molecules. And so to make sense of why you'd have 6 water molecules with a metal cation that has 3 positive charges, we have to look at more in terms of the shape of the final combination. Now the waters, they have a particular name, they're called ligands, and all these coordinate covalent compounds are going to consist of things like a metal cation and then some molecule that's got some additional electrons, like in the form of a lone pair. And then it just becomes a matter of how much space is there around the scandium, for example, to put those water molecules. Now the next slide, illustrates this a little bit further. So here, this first one, you saw that before in chapter 5. This is this complex ion. Remember, we started out, we had silver chloride, we said it was insoluble, we start adding nitrate to it, we make this complex ion, and now the compound is soluble. Well, what this is consisting of is you got the silver in the middle. It has 1 positive charge. Over to the right, we have an ammonia molecule. Now you recall, oops, didn't mean to do that. Okay. Then we've got another hydrogen and then another hydrogen. But the nitrogen has one pair of lone pair electrons. And then on the other side, we have another ammonia and it also has one pair of lone pair electrons. So we can get a coordinate covalent attachment going between the silver cation and the ammonia. But you can't really predict how many you're going to be able to put on there. But what we can say is that in this case, silver has enough space for 2 ammonia ligands to fit on there. But what we're going to see is it's not so much of the number of molecules that fit in there, but it's really going to be more of what's called contact points. And so for the nitrogen here, that one lone pair, that's one contact point. And then for the other ammonia, that's another contact point. So we have 2 contact points. We're going to, yeah, Lily, what's up?
Is the nitrogen the ligand or the whole NH3 molecule?
The whole NH3 is.
Okay,
Okay.
thank you.
You betcha. Now I'm going to erase what I've gotten up to this point so that I got a little more space. And we'll go to this next one. So for this next one, we've got oops. Oh, I see. I don't have my marker selected. We've got copper 2 plus. And now we're going to take 3 chlorides. Now these are just like chlorides in sodium chloride, calcium chloride, and in the compound copper chloride. Except in the compound copper chloride, there would only be 2. So that compound would have the formula CuCl2. But what we're doing here is not a compound. It's actually a anion, or excuse me, it's actually a cation, but it's a complex covalent cation. Put one more chloride over here. So now the copper has 2 positive charges. Each of these chlorides has a negative charge, so that's some excess electrons. So those are all making an attachment to the copper 2 plus. Now when you're done, notice that this still has a charge. I'm sorry, there's a typo there. It should be 2 positive, not 2 negative. In fact, all of these have charges because they are actually ions. But the reason why you have 4 chlorides or 4 ligands is because you can fit in there 4 contact points around the copper. And then for this next one over, I'm going to erase again. Now you've got cobalt, and cobalt has 2 positive charges, so 2 plus. And this is another case of where you have water molecules around it. So I'm only going to draw one of the water molecules. It's got 2 pairs of lone pair electrons. And it's going to have a connection between the positive of the cobalt and those excess electrons on the oxygen. So cobalt's got enough space for 6 contact points which means it also then has 6 ligands. But what we're going to see on the next slide is that the number of contact points and the number of ligands are not necessarily the same thing. Yeah, Jamie. Yeah, they are. Yes, I'll go back to what she said there a second. So Jamie was saying, are coordinating covalents and complex ions? Yeah, they are the same thing. Now, the thing is, though, when we did talk about coordinate covalent bonds when we had ammonia and boron trifluoride, and that one is not an ion. So I don't know if you guys, I'll draw that real quick. Remember the compound we had between boron trifluoride. Oh, I'm saying fluoride, I'm drawing on hydrogens. Sorry, guys. Okay, let's make a fluoride down here. We can get a compound between that and ammonia, so NH3. And it's going to use the pair of electrons that are on the ammonia, and it will make a bond between the nitrogen and the boron. But notice this does not have charge, so that is not an ion, but that is a coordinate covalent bond. But what we're going to be doing in this chapter is looking exclusively at coordinate covalent ions. Okay? So, give me a second here. Well, anyway, I don't know what's going on with this thing, but we'll just go to the next slide. So what this slide is showing us is that you can have a ligand that has 2 contact points. See, we got a lone pair of electrons on one of the nitrogens and on the other. So we've got 2 contact points. But it is only one ligand. And then this molecule, it can twist around and end up looking like this right here, where the 2 contact points, the 2 nitrogens, are facing this cobalt. And then we can have another one of these molecules up here, and then we can have a third one down here. So you've got 3 ligands, but you have actually 6 contact points around the cobalt. And again, this happens because you've got the right space around the cobalt to fit those ligands in there. And they're showing you how the names of these are written out. I'm not going to worry about you guys doing that. I think that's really beyond the scope of a general chem class. If you took a class in inorganic chemistry, you'd be doing that. Yeah, Lily, what's up?
That whole thing is that ethylene diamine, the whole thing?
Okay, let me erase. This right, oops. Okay, here we go. This is the ethylene diamine right here.
Okay. So they're
And then,
calling that whole thing a ligand?
yes, the
Oh.
ethylene diamine is a ligand, and then there's 3 of those on our cobalt 3 compound.
Oh, now I see it. Okay. I didn't see that before. I mean, I'm
Yeah,
looking at it, but it didn't click. Okay.
yeah, I know this stuff's all really new to everybody. But you see, the way they're writing the formula out for that, they are abbreviating. They're abbreviating this thing with EN. So that's why they've got EN. I said I wasn't going to get into the formulas, but I guess I kind of need to a little bit. And then they put a subscript of 3 to indicate that there's 3 on there. And then this whole thing together the cobalt plus the 3 ethylene diamines, that all together is your ion. Okay? So anyway, that's the way that would work. So the next slide is for hemoglobin. So I said that, these sometimes are biological molecules, and it's a way of having this iron atom in here available. And that iron atom can actually go back and forth between iron 2 plus and iron 3 plus. And that is how this goes about carrying oxygen to cells, carrying carbon dioxide away from cells, is because it has that ability, has that iron atom in there that can change its oxidation state, and that allows it to pick up oxygen atoms and carbon dioxide. So you notice that this one has 4 contact points. I'm going to draw circles around them. You got one at this nitrogen, one at to the other nitrogen. You got one more at this nitrogen, one more at this nitrogen. So there's 4 contact points. But there is one big, gigantic ligand, and that's what is called a heme, H-E-M-E. So the ligand is a heme. This is the one, it's found in, in vertebrate animals and as an oxygen carrier. So it's hemoglobin. Okay. Now we're going to see a little bit later on that there's a similar molecule that's found in invertebrate animals. It does not use iron. It uses a different atom, but it still does the same purpose. It carries oxygen to the cells and carries carbon dioxide away from the cells. Okay. So here's some more examples of these kinds of molecules or ions, I should say. And what I need you to be able to do is when you look at these, be able to count how many ligands you see and how many contact points you see. So for this one over here, you've got 1, 2, 3, 4, 5, and 6 water molecules. So that gives you 6 ligands. And each one of those is providing 1 contact point to the cobalt. So you can see those. Oops, I'm not drawing so well. So you've got 6 contact points. But then for this next one, this is your ethylene diamine. You've got 1 ligand here, another ethylene diamine up here, and then 1 more down here. So that gives us 3 ligands. But each ligand has 2 contact points, so that you end up with 6 total contact points. And then for this last molecule here, we've got 6 chlorides. Each one of those is providing a contact point, so 6 contact points, 6 ligands. Has anybody got a question on how I'm coming up with that? Okay, we'll go on a little bit further. So here's a couple more. This time our ligand is cyanide. And there are 4 of those. And it gives you 4 contact points. And then the other thing that this slide is pointing out is that this has a particular geometry. And that geometry is tetrahedral. remember when we did the geometry for methane in Chem 140, we drew it like this. And that's also tetrahedral. So you can see these are similar up here. And then for this one, the one to our right here, this one is square planar. And if I were to take this molecule and rotate it a little bit, then you'd have the platinum in the middle. You'd have the two ammonias at corners of a square. And then the chlorides would be at the other corners of the square. So we could draw a square around that, but it's flat on the page, so it's planar. So anyway, geometries you guys had in Chem 140. So not only do these have ligands and contact points, they do have geometry. Now here is chlorophyll, and notice that in the center here is magnesium. So these have, I don't know why this picture is showing up over here. That is just, I have no idea why that's here. Collaborate's doing something weird. But anyway, around the magnesium, there are 4 contact points, each coming from a nitrogen. So there's a nitrogen with a pair of lone pair electrons. And then, but it's only one big ligand. So it's one big organic-y kind of a molecule with a magnesium in the middle. And of course, we know chlorophyll is responsible for taking sunlight and converting carbon dioxide into oxygen. So the magnesium's ability to move between oxidation states is going to make that possible. And then, okay, we've got another one here to look at. This one is ethylene diamine tetraacetic acid. And I don't recall if we did we do the water hardness experiment in lab? I don't think so. I think that was, yeah, I believe we got into the, I think we went to online before we got there. So no, we did. You've not seen this before. But anyway, this is ethyl diamine tetraacetic acid. No, we didn't. Okay, thank you. I appreciate you telling me that because I did not remember. But this is called EDTA, and you see EDTA in a lot of products. It's going to show up in cosmetics, shampoos. Occasionally, I've seen it in food. It's not accepted in Europe, but I don't know. We like to live dangerously in the U.S., I guess, because anyway, we do put it in some food, and what it's good for doing is tying up a metal, usually some kind of metal cation. I'll just put a plus out here. So if we wanted to, what they call sequester calcium, for example, calcium cations, we would use this, and it would lock them up inside that big molecule, and the metal would no longer be available. So we put that into cosmetics, and I think that its purpose, I don't really know for sure, but I think it is to lock up metals that may be in the process of producing those cosmetics. So anyway, the ethylene diamine tetraacetic acid, or EDTA, it's got 6 contact points. 4 of those are an oxygen, and let's see, 2 of them are nitrogens. But it is still yet only one large ligand. And I believe we got one more example. No, we don't. I'm sorry. Okay. Well, I don't guess okay. I think I used to have a slide as a picture of the hemoglobin-like compound that's found in invertebrate animals. And in that case, it's got a copper in it instead of an iron, and it causes the blood of invertebrate animals to have a bluish color because of the copper. So anyway, for what that's worth. Okay, that pretty much is the end of our covalent ions. And we're going to move back into transition metals, but now we're going to be looking at how they are applied, what they're used for in technology. So I'm going to go to that on the next slide. So we said that transition metals can be used as catalysts. So this is your catalytic converter in your automobile. So prior to the converter, that's where your engine is, you know, and your engine is producing, to some extent, dirty emissions. And that would be things like carbon monoxide, certain nitrogen compounds, and we don't want those going out and us breathing them. So what this is going to do is it's going to convert the carbon monoxide into carbon dioxide, and it's going to convert the nitrogen compounds into nitrogen gas. So you can see that we have rhodium as one of our transition metals. That's really expensive. We also have palladium, which is not as bad as the rhodium, but you know, all of these are very expensive materials. That's why it's worth someone jacking up your car, climbing under there and cutting the catalytic converter out and running away with it, because these things are expensive. Or if you've been the person who had their catalytic converter stolen, you know how much it costs to replace it. So that's because of the presence of these metals. Now it says that there's some other catalytic materials. It could be platinum, cerium to a small extent, iron, which would not be very expensive, and manganese, which would not be very expensive. But all of those are responsible for doing reactions like converting carbon monoxide into carbon dioxide, or these nitrogen containing compounds into nitrogen gas. So that's one application of transition metals that's important to us. This next slide is the beginnings of talking about magnetism. And you're going to have 4 words that you're going to need to memorize. I'm sorry, but you do need to know these 4. And so we're going to be explaining what they are, and anyway, you can get it from that. So our first word is paramagnetic. And we can think about the para part as being not. It's not magnetic. Oh, sorry, I just got the message that my signal is weak, so I'm going to turn my camera off. Okay, anyway, to have magnetism, the prerequisite for that is to have unpaired electrons. That's the first thing you have to have. If you don't have unpaired electrons, it's just not going to be possible to have a magnet. So if you remember when we did orbital diagrams back in Chem 140, you would see things like boxes representing different orbitals. So let's say that we're looking at the p orbitals, and you would have 3 of the p orbitals. Well, if you had electrons in all those orbitals, one electron would be pointed up, one would be pointed down. The spins would be up and down and up and down. But if instead we had p orbitals where you only had one electron in each of those orbitals, then it could look like this. But those are actually independent of each other, those orbitals. They're at the same energy level, but they are independent of each other. And therefore, the orientation of the spin of that electron can actually be random, like what we're seeing over here in the left side. So over here, there's unpaired electrons, but they are not going in the same direction. So that's our other requirement for magnetism, is the spins must be in the same direction. That's what's going to give you a north and a south pole for a magnet. Okay? Think of a magnet, we think about one pole being north, one pole being south. But for that to be the case, you need an arrangement like what we have here on the right, where you have unpaired electrons and their spins are all going in the same direction, making one end north and one end south. Now we've got a new word for this, and that is ferromagnetic. So it's not that ferro means that it is magnetic, but it is magnetic. The ferro means that they are every one of the electrons is aligned in the same direction. We're going to see in the next slide a sort of intermediate situation for this, and also a well, anyway, what to get the next slide. But anyway, what's on the right is magnetic. What is on the left is not magnetic. So paramagnetic, not magnetic. Ferromagnetic, it is magnetic. And these kinds of magnets would involve these kinds of elements: iron, cobalt, and nickel. So now let's go to our next slide. And we're going to see 2 more possibilities. There's antiferromagnetic. So this is meaning that all the spins are equal, but they are arranged in opposite directions. And because of that, they're going to cancel. So we've got one up, but we have one down. And it just keeps repeating that pattern. So they cancel out. So this antiferromagnetic would be not magnetic. And then we got one, and before I do that, the materials that could produce a antiferromagnetic material would be the ones in that list there: the chromium, iron 3 oxide, a really odd compound in the middle, and manganese oxide. And then what we have on the right then is what's called ferrimagnetic. So it's not ferro, it's ferri. And these are, we will not say that these are magnetic or not magnetic. They are slightly magnetic. They're in between. Well, I should have started that word somewhere else. But anyway, it's slightly magnetic. It's not totally magnetic. It's not totally not magnetic. It's just kind of in between. And what you have happening here is the spins are opposite. This one's going up. The one next to it is going down. But you notice the size of the arrows are not the same. The one going down is smaller. So even though it cancels, it only cancels a fraction. So overall, the material comes out being magnetic. So a little flash back through these. If it's para, it is not magnetic. The spins are all random. They are not oriented towards each other at all. Ferromagnetic, it is magnetic, and they're all going in the same direction. Next case is antiferromagnetic. This would be not magnetic because they cancel. For every up, you've got a down. Then for the ferrimagnetic, they are, paired up, one down, but they're not the same magnitude. So this one going down is only going to cancel part of the one going up. So has anybody got a question on this whole magnetism thing? Okay, not getting anything there. So that was the last slide on this chapter. Okay, so we're going to be going to our last chapter. That's nuclear chemistry. And we may finish the chapter tonight. I don't know. We'll see what happens. And then we're going to have, let's see, next Monday would be lab day, but we don't have any labs remaining. So we will either finish this chapter and review, or we'll just review. And then you'll have your exam 4 on Wednesday, a week from today. So anyway, let's go look at our last chapter. That's nuclear chemistry. So this is chapter 21, nuclear chemistry. And this goes with the lab that we did on Monday. So we know from that lab that we have these things called isotopes. We talked about this some in Chem 140, that all of the atoms of one particular element are going to have the same atomic number. That is, they're going to have the same number of protons. And if it is not an ion, it'll have the same number of electrons as it has protons. But how the isotopes vary is their mass number. And the mass number is always going to be equal to number of protons plus the number of neutrons. Of course, neutrons have no charge, so we don't mention that. So as it says below that, nucleus is composed of two nucleons, or two different kinds of particles, protons and neutrons. Number of protons is the atomic number. If we have a different number of protons, it would be a different atomic number, and it would be a different element. Okay? Number of protons has to be the atomic number. If we change the number of protons in some way, then we now have a different element. And number of protons, neutrons together is the mass number. So we did some of this in the lab on Monday. Okay? Now, the question that we get into is, well, why do we even need neutrons? What good are they? Okay, What is the point of those? And the reason why they exist is going to be on this next slide, the reason why they're present. For some of the lower atomic number elements, we can have, say, 2 protons. So this would be helium. Well, those 2 protons are both positive. So they are going to want to repel each other, and this is going to want to come apart. That's one way of looking at it. Now, imagine if you could have 2 protons, except I'm not going to put a P on there because these are not really going to be protons, but protons that have no charge. Then they are going to be attracted to each other, similar to what happens with gravity. It's not the same as gravitational force, but it's a similar kind of thing. So if I had protons that had no charge, they would be attracted to each other. Now let's say I've got neutrons. Here's one neutron. Here's another neutron. They are also going to be attracted to each other, and there's no repulsion because they have no charge. So they're going to be attracted to each other, just like with gravity. So now let's put these all together. So now I've got a proton, another proton. Oops, not drawing so well. Those are attracted to each other. We've got a neutron here, another neutron here. All these particles are attracted to each other if we forget about the protons being positive. But the protons are positive, so those are repelling. But the idea is that there is enough attraction between the protons and the neutrons to hold all this together, in spite of the protons having the same charge and repelling each other. Anybody got a question on that part? So it works out that if we have the same number of neutrons as protons, it's going to be stable. The particular element is going to be stable. But that's only going to be good up to a certain atomic number. And then it no longer works. You actually need more neutrons to make the atom stable, or to make the isotope stable. So you're needing more neutrons. Now that's occurring above this line. Now the line, this line going like this is what it would be if you had the same number of neutrons as you have protons. And that's the case down here when the atomic number is less than 28. But as soon as you start to get above 28, you're needing more neutrons, and you need progressively more and more neutrons. So you start to deviate more and more off the line here. And that's what's occurring up till you get to a mass of, you get to a atomic number of 83. And that is, I'm having trouble seeing it, it's right here. At that point, no matter that you have the additional neutrons, everything out here is not really stable, and it doesn't hang around very long, and it has to decay down to a situation where you have fewer protons and you can have enough neutrons to make it stable. So in this part, the number of neutrons equals the number of protons. In this part up here, you have more neutrons than protons until finally you get to the point where even having those additional neutrons will not make it stable. Anybody got a question on that? So this is the reason why certain elements on the periodic table aren't really gonna, they're not stable, they're not gonna hang around, and they had to be artificially produced. They do not occur in nature. And this next slide is sort of showing what I'm talking about there. And that is, well, it's calling it binding energy. Binding energy is that attractive force between the neutrons and between protons if we forget about the repulsion because of them being positive. So across the bottom here is the mass number. So what this is saying is that up to a certain mass number, which is about 60 here, elements would like to have more protons and more neutrons. But finally, you get to the point to where it's too much. They don't want to hang together, and they want to break apart. So that's what you got over here at these mass numbers. So that produces this situation of where if you're over here at one of the ends where these are very unstable, they want to break apart. Break apart is called fission, so that you can move to a lower mass isotope. And then fusion is where you want to combine together and make a heavier isotope. And then it hits the highest occurrence there in that vertical line I drew in. So this is what causes our various nuclear reactions to occur. And that's what we're going to be spending most of our time on this chapter. But does anybody have a question? Okay, so this next slide, it shows you the various particles that you can have when you have an unstable isotope and it is decaying. First one we see here is an alpha particle, and it is either this isotope of helium, where you got a mass of 4, so you've got 2 protons and 2 neutrons, or sometimes they'll write it this way where they'll use a alpha symbol with the 4/2. Another decay particle is a beta particle, and it is an electron, just a regular old electron, but well, not regular, because it is, as it says here, it's high energy electron. So it's moving really fast, but it is an electron. Another way it's represented of using the E, they use the beta symbol, but you'd still have the same numbers. And I just noticed that there is a typo. That should be a -1 there, not just a 1. The beta is correct. Then we can have a positron. That is an electron, but it has a positive charge. So we could represent it with this symbol, except you have a positive sign on, on the number there. Or they can use the beta and just have a positive on the symbol there. We can have a proton as a decay particle, and you could represent it either with the hydrogen symbol or you can have a P for proton. The idea with this is if you took a hydrogen atom, it's atomic number 1. It's got 1 proton, 1 electron. If we took away its 1 electron, then its charge is going to be positive. And also, it's only going to be a proton. There are no other electrons. So a hydrogen ion or a proton is the same thing. Then the next one we have is a neutron. Notice this atomic number is 0, but it does have a mass of 1. And then gamma ray is our other decay particle, and it does not have mass. It does not have. I don't know why my phone is ringing. Sorry, guys. Anyway, so it's given this symbol, and that's the gamma symbol, or gamma symbol, and we're not going to know that it's present in a process. So pretty much that has to be, you have to be told that, because you're not going to be able to figure that out from looking at a nuclear reaction. And so that's where we're heading now, is into nuclear reactions and what they look like. They are similar to chemical reactions. You still are balancing equations. It's just that what's involved is not a chemical process, but it is a nuclear process. So our first one that we're going to look at, our first decay process, is one that produces an alpha particle. So that we saw before, it could be either helium symbol 2/2, or it can be alpha 2/2. So mass of 2 and atomic numbers 2. So the way this would occur is you'd start out with uranium-238. And the uranium-238 is becoming thorium-234. So in the process of that, oh, I'm just realizing I'm doing that wrong. It's going to be 4/2, not 2/2. I thought something seemed wrong. Yeah, 4/2. In the process of going from uranium to thorium, the mass number goes from 238 to 234. Well, the 4 difference is in the alpha particle. Okay? And that's the way all of our nuclear processes are going to go. We're going to be clicking through them here in a moment. And I think it'll be a little more obvious once we do a few of them. And then we're also going to do a worksheet. But what I want to talk about next is how we identified alpha particles, beta particles, and gamma rays. So that's on this next slide. So the idea here is we had a radioactive substance. We had something that was going to decay. And the way that people initially found out that there were materials that did this was, you've probably heard the story, Madame Curie. She was doing experiments with uranium, and she put them in a drawer to store the material for the next day. And she also had photographic plates in there. I don't know why she would have had both of these in the same drawer, but she did. And so at the time, they knew with photographic plates, you expose them to light, you could produce an image. Well, she had these photographic plates. She came back in later, and there was an image on the plate, but it had not been exposed to light. And she was able to figure out, well, there must have been something in the uranium that was like light, that was like a photon of light, and that caused the reaction to make the image on the plate. So that's how they figured this out initially that there was decay particles. But then they needed to take it further and try to know a little bit more about those particles. So they set up an experiment like what we're seeing here, where you have your emitter of your radioactive substance, you have your photographic plate on the opposite side where you can make an image of the decay particles. And then in between there, you have one plate that has a static positive charge and another plate that has a static negative charge. So, the top plate's staying positive, the bottom plate is staying negative. They noticed that some of the spots that they were getting on their plate were not in the middle. Some of them were to the top, being attracted to this positive plate. So they realized there had to be particles that were negative. So those were your beta rays, or those were your electrons. Then they saw there had to be a particle like the alpha particle that would be attracted to a positive charge, or excuse me, they were positive and they were attracted to a negative plate. So you saw spots down here. Then they had some spots that were appearing in the middle. They realized that these were not positive or negative, and so that was the gamma rays. So that's how they figured out some of the information about the different decay particles. Now there was more going on than this, but I think this is as far as we want to go with how they discovered these. So on the next slide, we're going to look at the different decay processes. So this first one we've already seen, that was an alpha decay. And we have that process written out here, where there is a particle that releases an alpha particle and makes a new isotope. And then for beta decay, we have a radioactive isotope. It releases a beta particle and makes a new isotope. And that's what we're going to be seeing through all these gamma decay, positron emission, electron capture. Now we're going to do each one of these separately, and they're going to be bigger and easier to see, so we'll just wait till we get to that, although I'm looking at my next slide and oh my God, they're totally messed up. Okay, that's not going to work. So we're going to have to do something different here. Okay, what I'm going to do is we're going to drop out of this presentation. I'm going to share my screen and we're going to look at the slides that are in Blackboard, because Collaborate has totally mangled up. Oh my God, just to show you what it looks like. It made this out of them, so that's not useful at all. So we're not going to do that. So let's get rid of that. And let's go to sharing my screen. And then I'm going to go into Blackboard and we'll just look at the presentation there instead. So I'm going to go here. And only problem is I can't draw on the slides. So that will be the downside of doing this. So we'll pop back into the other presentation after we get done with this. So where we dropped off was here. So now we're going to look at this first decay process, alpha decay. This is what that slide was supposed to look like. And our alpha particle is shown here, helium 4/2. And we're starting with uranium-238, we're making thorium-234. So the atomic number of uranium that you would get if you looked at the periodic table is 92. If you needed to know the identity of what has an atomic number of 92, you'd look on the periodic table and go through the atomic numbers. You would find uranium. Its mass number is 238. After the decay, you now have a new element. You no longer have any uranium, you have thorium. The reason why it's thorium is it has a different number of protons. Instead of having 92, it's got 90. Also, during that decay, it lost a mass of 4. So now it's gone from 238 to 234. Now you can account for those changes by saying, okay, it's an alpha decay where you've got a 4 over a 2. Like it says here, note how the equations balance. If you look at the mass numbers, 238 on the left, 234 plus 4 on the right. So 234 plus 4 gives you 238. Or if you're looking at the atomic numbers, we got 92 on the left, you got 90 plus 2 on the right. So 90 plus 2 is 92. So you got the same number, so it balances. Now this is kind of important. Does anybody not get what we're doing here? How we're balancing these? Because the idea here is that if you know two of these, say you know the uranium and the thorium, you could figure out what the particle is. You could figure out that that's an alpha particle. Or if you knew that it was uranium to start and that there was a alpha particle in the decay, then you could from that figure out that the new isotope has to be thorium. So we're going to be doing this on a worksheet here in just a moment, so I'll make sure you guys are getting that. Okay, let's look at our next possibility here. This is a beta decay. So we've got iodine 131. So its mass number is 131. Its atomic number is 53. After the decay process, we now have xenon. The atomic number went from 53 to 54. So it actually increased. The mass number stayed the same. So what would fit that kind of observation is that it has to be a beta decay or an electron. So that we have a mass of 0 because 131 and 131 are the same numbers. Therefore, it has to be 0 for it to balance. And the atomic number for the beta particle, -1, because you're moving from 53 to 54. Or we've got it, at the bottom there where it's talking about balancing, that 31 is equal to 131 plus 0, and 53 is equal to 54 plus a -1. Anybody got a question? Okay, I'm not hearing anything, so I assume we're all right. Then next one is positron emission. So we're going from carbon 11 to boron 11. The mass didn't change, so therefore there must be a decay particle that has a mass of 0 since there's no change. The atomic number changed from 6 to 5. And for it to change from 6 to 5, then our particle has to have a mass number of 1. Again, what we're going to be doing is, in some cases, we're going to know that it's boron and you're trying to figure out that it's a positron, or you know that you're producing a positron, so you're needing to determine that the new isotope is boron 11. Okay, let's look at another one. This one is a little bit harder to figure out when we're looking at it, because you see the particle is not on the right, it's on the left. What's happening is the nucleus is actually capturing that electron and it's becoming part of the nucleus, so that the atomic number decreases by one, excuse me, and the mass though stays the same. But again, we just look at the numbers, and if we can balance the numbers, then we can figure out what's going on. Our next one is neutron emission. This is different than what we've seen before. Now, instead of one particle decaying into two particles, we have two particles combining and making something new, and also releasing some decay particles. So we have californium-249. It's combining with oxygen-18, and it's making this new isotope. Again, the numbers have to all add up for it to work. And I don't know if there's one more or not. Nope, there's not. So I wanted you to see these in a form to where you could actually read them. So I'm going to go back now into the presentation inside of Collaborate. So I'll stop sharing my. And actually, what I want to do at this point is we're going to go to the worksheet. So let's do that instead. And let's see. I guess I really should go back to sharing the screen for just a second here, because we need to. First off, you need to see where to get the worksheet. So you go to course materials, scroll down to worksheets. We're on this last set, nuclear chemistry, and we're doing this one called nuclear equations. So this is the worksheet that you're going to be using. And what you're wanting to do is figure out what are the answers where there are question marks. Okay? Now, notice that there are question marks not just for the particle, but also for some of the numbers. For instance, can't mark on this. So, but if you look over here on number 5, you can see that you've got an atomic number that's got a question mark. It's missing. So to figure that out, you'd have to go find that element on a periodic table and put it in, and then you can go on and balance this. Because if you don't have that information, it's impossible to balance. And we have these first 8 here. The reactions are actually written out, and then for the remaining ones, the remaining 10, it's in words. So sometimes these words get confusing. So we'll have to work our way through that. But anyway, you can get that over here at worksheets and Blackboard. You're going to need a periodic table, so you can click on periodic table, and there'll be a periodic table if you need it, or when you need it. So now I'm going to go back over here and stop sharing. And what you'll want to do then, again, is get to the nuclear equations worksheet. So I'm going to put it up here again, except I'll do it in this place. And there's some information you want to read through before you get started. But then I'm going to need for you guys to answer. I think the first one was at, I think it was 11, seems like. Okay, where did I put that? Hang on a second. I made a note, now I can't find the note. Yeah, number 11. So let's see, for 11, so we got Neptunium-233 is formed when Americinium-237 undergoes a nuclear decay process. So let's see, that's going to be 237.95 AM. 37, oops, hang on a second, I'm going to try to type into this thing, see how that goes. 237, and then 95 is the atomic number. Then I'll move that over. And then it's americinium, so AM. Let's move it. Oops, come on, stop that. Okay, so we got that much. And then we need an arrow. And then we're going to need the Neptunium-233. So, see, 233. Put that here. Oh, sorry. When I click, it just goes nuts. That's atomic number is 93. Oh, okay. Atomic number is 93. And oh yeah, yeah. Sorry, I'm blanking here. Oh boy, that just is terrible. So this is going to be NP symbol. Oh, sorry, I keep getting the wrong tool. There we go. So now we need a plus, and I'll move that one over. So now this is what they've told us. We just don't know how to do the rest of it because they don't tell us what the nuclear decay process is. So what we need to do is figure out what would we add to 233 to produce 237, right? So that would be a 4 for the mass number. And I don't know who asked me the question because they texted me, but I don't know their number, so I don't know what person that is. So hopefully I'm answering their question. But anyway, if you add 4 to 233, you get 237. Then we need to figure out, well, what do we add to 93 to make 95? And that's obviously going to be 2. And then I'm going to move that over, so that is a atomic number. So we got 4 over 2. Now, sorry. So that should be obvious that this is going to be a helium or it's going to be an alpha. I don't have a good way to type an alpha, I don't think. So I'll just do a helium instead. So and so that would answer our question right there. I don't know who was asking this one, but hopefully I've answered it for you. Does anybody have a question on how we do that? And the whole point is that you're going to you write down what you know, and they told you what was formed. Now this is the part that might be a little tricky. When they say something is formed, we tend to take whatever is the first thing in the sentence and put that down as the first thing we write, but instead we should look to see that's formed when the americinium undergoes. So the americinium is what is our reactant. That's what we're starting with. So we put that down first. with its symbol. And then from its symbol, we look on the periodic table, get its atomic number is 95, and they tell you the mass of it's 237. So that's how you get that isotope symbol. Then we need to get the isotope symbol for the neptunium-233. So you look it up on the periodic table, you see that its atomic number is 93, so that's where the 93 came from. They tell you the 233, you have to put in the symbol. So that's how you get those. And then you just figure out, well, what numbers do you need to make this all balance? So to get a 237 from a 233, you have to add 4, and to get a 95 from a 93, you have to add a 2. Then you take the 2 and figure out what does that correspond to, and that would correspond to helium, or you should also know that it corresponds to an alpha particle. So has anybody got a question on that one? And then there was a question on, I think it, oh, now I don't remember. Let me look back to the text a second. I'll figure that out. Okay, it was question 14. So let's look at that. Okay, neon 22 is formed when an element undergoes a beta decay. So we could first just type in Ne for neon. We're told that the mass is 22, so let's put that in. And I'm going to move it over a little bit. And then we need to look at the periodic table to get the atomic number for neon. And that is 93, I believe. Let's see, am I right? That doesn't seem right. Hang on a second, let me look here a minute. No, it's 10. What am I saying? I'm sorry, I'm looking at the totally wrong place here. Okay, so it's a 10. Is its atomic number, and then we'll pull that over so that we got our atomic number, and it says neon 22 is produced when element undergoes a beta decay. So we'll need a plus, and then we'll need to have a beta decay. So a beta decay is an electron. So we'll put in the symbol for that. Oops. Need to move it over a little bit. Oh, not like that though. And then its atomic number is a -1. And it has no mass, so therefore its mass is 0. And so now we just need to take those numbers and figure out what's the values for our isotope that we're trying to determine. Oh yeah, we do need an arrow also. I'll put that in. So if we have 22 and 0 on the right side, then our mass number must be 22. And if we have, let's see, 10 plus a -1 gives us a 9. I'll move that over. And then I can take the 9 to figure out then what the identity of the element is. And that would be fluorine. Oops, it's not clicking. That didn't do anything. Happen. Okay, one more time. Fluorine. There we go. Okay, so now that's your reaction there for that one. So does that make sense to you guys? Anybody got a question? Okay, so I'm going to go ahead and shut this part down. I'll be posting the key so you can, if you want some more details on anything. So what we ought to do now is go back to the, oops, wrong place. Let's go back to the presentation. And we left off with these messed up, equations that Collaborate decided to just go nuts with. But then the next slide, it looks like it's okay, and that's this slide. And this is depicting what's called a decay series. So the idea is you're starting here. I'm going to have to blow that up a little bit to see it. Blow it up a little bit more. Okay, you're starting with uranium-238. And they tell us at the bottom of this chart, or not the bottom, but sort of the middle, that if it's a green arrow, it's an alpha decay, and if it's a red arrow, it's a beta decay. So we've got a alpha decay here to thorium-234. That was one of our example reactions. That is then followed by a beta decay to here, which is followed by another beta decay that takes us to uranium-234. So notice what's happening is during these decays, our masses are decreasing. That's because we have an unstable mass and it has to resolve to a lower value. So then it's just going to keep on doing that where we are, going through, these alpha decays. Then we've got another couple of beta decays. We have one more alpha, a couple more betas. And then we finally end up with lead 206. At that point, our mass number is such that it's going to be stable enough to hang around. So this is just showing how these decay processes are going to resolve. Our next slide gets into something that's called half-life, and we're going to see on the next slide what this is useful for, but first we need to talk about what it is. So we have a radioactive isotope, cobalt-60, and we start out with 10 grams of it. And if we look at what time period it takes before we have lost half of that 10, going to 5, then that is, let's see, one half-life, which they're telling us is equivalent to 5.27 years. Now we put the same information over here in this table. So at time 0, we have 10 grams, and that's 100% of our sample. And then during the time of one half-life, which is also 5.27 years, the mass remaining is now 5 grams of where we started. So that's 50% of what we started from. Then half of the 5 grams decays, and we're left with 2.5 grams of the cobalt-60. So that is a second half-life, or if we're looking at the table over here, that's a time elapsed of 10.54 years. The mass remaining is 2.5, or if we think of it in terms of percents, it's 25. And then it just keeps on going from there. Now you may be thinking, well, what do I do with this? Well, there's a couple of things that we could do. If we had the if we knew the mass, oops, sorry, my marker quit. If we have the mass, and then if we have the time period, we can then calculate what is the length of a half-life. So that first off, you have to look at the mass and see when does it become half of the previous mass, and it does at this step right here. Went from 10 to 5. Well, it did that in 5.27 years. So at that point, we think it's probably 5.27 years. But to be sure, we could look at the next row where we're going from 5 to 2.5, so that's half of the previous mass. And then we look to see what's the difference here in time. The time difference is 5.27 years. So by looking at our data, we can establish that our half-life is 5.27 years. Now that's one thing we could do. Another thing we could do with this is if we knew the value of a half-life, if we knew that it was 5.27 years, and we knew how many half-lives have gone by, and we knew what we started at, we could calculate what is our current mass that we have. Well, that's the two problems that pop into my mind. There's some other things, but we're not going to get into those because they're just a little bit more difficult to do. So we'll keep it to this. This is, I think, sufficient. Anybody got a question? Okay, our next slide. This is the application of this whole idea of half-lives. If we have an organism, whether it be a animal or a plant, and it's alive, then the ratio between, I need to blow this up a little bit so we can see it. The ratio between carbon-14 and carbon-12 is constant. That's what it says there. It is constant. But when those organisms die, namely, if we take the cow and make an artifact out of the leather, or if we take the tree and make another artifact out of the wood, then they're no longer living. And at that point, the carbon-14 continues to decay, but the carbon-12 is not going to decay because that's a stable isotope. So that as time goes on, the ratio of carbon-14 to carbon-12 changes. And we know the decay rate of the carbon-14, and so we can then calculate how much time has elapsed. And that is how we do radiocarbon dating that you guys have heard about probably many times. We can from that we can get how much time has gone by since that living organism became a product, you could say, no longer living. So we can see less carbon-14, more carbon-12, and that changes that fraction. Anybody got a question on that? Because that's one of the happier, well, what we're going to get into next is we're going to get into nuclear fission. And nuclear fission can be a happy process. We can produce electricity. That's a good thing. You know, we're not creating carbon dioxide. And if we can dispose of the waste in the proper way, then it actually would be beneficial to do. On the other hand, we can also use it as a way to blow people up. So that's the bad side of it. So we're gonna discuss both aspects of that. So what this involves, nuclear fission, is that we have a unstable isotope of uranium-235. It's already unstable, but we then impact it with a neutron. And when we do, we make this very unstable nucleus, uranium-236. It is then going to split into two what was called daughter nuclei. So barium-141, krypton-92. And it's going to produce a significant amount of energy. However, that's not what makes this process so energetic. What makes it so energetic is that it's also going to release, in this case, 3 more neutrons. Now, if we'd have gotten different daughter nuclei, we might have only gotten 2 neutrons. But in any case, we're going to get more neutrons. So if we look at the overall process, we put in 1 neutron and we got back 3. So we got back 2 more than what we put in. Then if we take that and apply it to more isotopes, we can get a situation like what we're seeing here. This is the first part of the process that we looked at. And then if each of those neutrons goes on to find, let me make it bigger, if they go on to find more uranium-235, such as here and here and here, we can produce a whole lot more daughter nuclei. I'm not going to read all these off, but anyway, make all those, and you can see that while we're doing that, we're making 3 more neutrons, 2 more neutrons, and so on, like I was talking about. And then if we can capture those neutrons, if we can not capture, if we can allow them to continue to impact more isotopes, then this will become a chain reaction. That's what we're going for, is a chain reaction that is sustainable. No, this nuclear chain reaction. So let's go to the next slide, and I'm going to make this smaller. Now for this to work, we need a certain mass of isotopes. We need a certain number of those, so that when a neutron comes in from the outside, it starts hitting all these isotopes, and they keep making more neutrons. They keep impacting other neutrons. And even though some escape, like we see here, most of them are successful, and we're going to produce a significant amount of energy. On the other hand, if we have something less than the critical mass, the subcritical mass, then we can see that a lot of our neutrons are escaping. They're not going on to make more of these processes, and so that chain reaction will shut down. Okay. Now I see that it's actually after 9 o'clock, and we're not been taking a break, so I think that it would be reasonable to just go ahead and we'll shut things down at this point, and we'll come back to this slide on Monday. So anyway, unless someone's got a question, anything? Didn't expect there to be. Okay, well in that case, you guys be as safe as you can. Take care of all of your people, your friends, and your family, and yourselves as best you can. And I'll see you on Friday. So have a good evening.